Good evening. This is going to be section 10.4 of your textbook. It's the title of it is Acid-Base Equilibrium, which is, given the title, you should probably guess that it is a pretty central theme in chapter 10, since chapter 10 is acids and bases in equilibrium. Well, it is a central theme. It's very important, especially important in biochemistry. We're going to talk about this hemoglobin thing, the equilibrium between hemoglobin and oxygen. Just in short here, in your body, in any vertebrate body, and actually there's actually a sort of hemoglobin type thing in plants, although it's how related it is to vertebrate hemoglobin is not really quite clear, or wasn't when I was studying it. But you have hemoglobin. It's a protein, and it contains its 4 subunits. Each subunit contains an atom of iron, which is complexed by what we call heme, H-E-M-E, and oxygen will bind to it when pressure of the oxygen is high. And that hemoglobin, it's in the blood, in red blood cells. It's going to be transported through the circulatory system to the places where it's needed. And of course, where it's needed is going to have a fairly low oxygen concentration because you use oxygen to generate energy. You'll see an oxidative phosphorylation where oxygen plays a role there. And there's little oxygen around, so the oxygen is going to be given off. It's what we call an equilibrium thing. If you have a lot of oxygen around, the hemoglobin binds oxygen. And if there's not a lot of oxygen around, the hemoglobin is going to give up some of the oxygen. Some of the oxygen is going to go off into the surroundings, where, of course, it can be used. We'll see that later on we'll be talking about that later on in the chapter. But we're mostly talking about acids and bases here, and acids and bases do exist in water solution in what we call an equilibrium. And there's also something called Le Chatelier's principle to determine what happens, which determines what happens when there's some sort of a stress on the equilibrium concentrations. So we'll see that over the next, how long? Usually around 20 minutes here. In an equilibrium reaction, 2 reactions take place, forward reaction and a reverse reaction. So far, you're probably used to seeing reactions that are written like the forward reaction here, HF plus H2O. They're both aqueous, of course. Water is the liquid, it's the solvent. Going to fluoride and hydronium ion. And you've also seen that hydrogen fluoride is a very weak acid, so we're showing an acid dissociation of hydrogen fluoride. We've said it's a weak acid. It doesn't dissociate much. So what you have in solution is mostly hydrogen fluoride and a little bit of fluoride and hydronium ion. Well, the reaction can go in the reverse direction, and the reverse direction is given here. And what's happening in a reversible reaction in an equilibrium situation is that both the forward and reverse reactions are going on all the time. They're going on at rates such that there will be a constant for a given concentration of, if you put a given amount of hydrogen fluoride in a given amount of water, there will be at equilibrium a fixed amount of, and constant temperature and pressure, there will be a fixed amount of hydrogen fluoride and fluoride, and of course, hydronium ion. That doesn't mean that the reaction is not going on. Both reactions are going on such that the forward reaction is taking place as fast as many molecules of hydrogen fluoride are dissociating to give fluoride and hydronium ion, as fluoride ions and hydronium ions are reacting to give hydrogen fluoride and water. These aren't necessarily, you already know that hydrogen fluoride is a weak acid. So there's really not a lot of fluoride, but it's going back and forth the whole time. And here's another diagram. This is, you see this in just about every chemistry textbook, this diagram or something very similar to it. The only thing different is going to be the specifics of the labels are going to be a little different. But still, you take an initial condition, which is usually going to be, you take we're talking acids and bases, and we're talking about hydrogen fluoride here, so let's talk about acids. You take an acid, you add it to water. That is the reactant. Time is equal to 0. So that dotted line there on this graph, the dotted line, the reactants, the dotted line where it joins the vertical axis. You add it to water, and at that instant, it's going to start reacting, and the concentration is going to start decreasing. And as the concentration as the reaction progresses, the concentration of products increases, and the concentration of reactants decrease. And eventually, you're going to come to an equilibrium where there is no change. You cannot measure any difference in the concentration, even though the reaction is taking place at all times, because the rate of the forward reaction is equal to the rate of the reverse reaction. That's going to be just one kind of definition of equilibrium. We'll go through this, and I'm going to give you a little something extra. But let's go back. Two are taking place. Okay, look at the equilibrium is reached when there are no further changes in the concentration of reactants and products, and the rate of the forward reaction is equal to the rate of the reverse reaction. You keep those in mind. So let's look at this learning check. Before equilibrium is reached, the concentrations of the products what? Well, they don't say are or is or anything like that. So equal, not equal. Well, before equilibrium is reached, you already know that there's not necessarily equal or not equal in this case. That's really not relevant. Equal and not equal. Concentrations of reactants and products aren't necessarily equal in any equilibrium process. So reactants and products, the concentration of reactions and products change. Remember I showed you here, you start off with a high concentration of reactants, and the concentration of reactants decreases and the concentration of products increases. So there's a change there. They're changing. And B, initially reactants have a rate of reaction, something then, so it's got to be faster or slower. It's got to be one of those, unless they're really playing tricks with the words. So it's faster or slower. Well, initially, what's initial? They even give you the rate of you can get the rate of reaction from the slope of the curves that indicate the concentration of reactants in products with time. Well, when you initially, in this case, there are no products, so the rate of the reaction has to be faster. The reaction of reactants has to be faster than the rate of the reaction of the products, which is very slow. It's it's going to take a while to build up until it gets to the equilibrium concentration. At equilibrium, the rate of the forward reaction is, what does this tell you? At equilibrium, what's the rate of reaction? Well, there's a rate. The reaction does have a rate. There's a reaction, but but they're equal. We just define it's equal. You have to have the same number of reactants going to products as you have products going to reactants. So the rate of forward and reverse reaction are going to be equal. And at equilibrium, the concentrations of the reactants and products, well, either they change or they do not change. Equal or not equal. Equal and not equal in equilibrium really is not a really good measure, you'll find, because an equilibrium process can lie in all the way towards products, all the way towards reactants, or anywhere in between. So really, at equilibrium, the concentrations of the reactants and products do not change. So you have before equilibrium, they change. Initially, the reactants react faster than the rate of the reaction of the products. At equilibrium, the rate of the forward reaction is equal to the reverse rate, and at equilibrium, the concentrations of the reactants and products do not change. And so what do we get here? There's your answers to that. Got one more slide here, and I'm going to go into something else. Not go into something else. I'm going to do a kind of a sidebar. When we alter the rate, the concentration of a reactant or product of a system at equilibrium, when you alter the concentration of one of these, just one, or you could actually, in principle, you're mostly responsible for knowing about what happens with one, because if there's more than one, then the math can get a little complicated, but it can be worked out. The rates of the forward and reverse reactions aren't going to be equal anymore, because if you add reactant, there's going to be more reactant than the equilibrium concentration, so it's going to want to go towards product. And the same is true if you add product. The reverse reaction is going to take place to reinstate that balance. And that is essentially the meaning of Le Chatelier's principle, where when the equilibrium is disturbed, the rates of the forward and the reverse reactions change to relieve that stress and reestablish equilibrium. And it's not necessarily adding or removing reactant or product. It can be changing the temperature, it can be changing the pressure. There's a few variables you can use to affect that. But I'm going to switch to the whiteboard now. I'm going to show you something that hopefully will not confuse you. Hopefully will actually make it a little easier for you to work some of these problems. When we do equilibrium, there is something called an equilibrium constant. And I'm going to do the equilibrium there's the equilibrium constant. You're really not responsible for knowing this. I'm putting it up here as just as an explanatory thing, so you see how you can work through this, how this makes sense. And let's take this reaction, the one we're using here. It's fluoride. It's going to be aqueous, plus H3O plus, which is going to be aqueous. The way an equilibrium constant works, and this is the acid dissociation constant of hydrogen fluoride or hydrofluoric acid that we're talking about here. So I'm going to write it the way you would see in a textbook. It is equal to, this is for HF in water. The concentration of fluoride times the concentration. Remember these brackets, they mean concentrations. And I'm going to move this over a little bit. Okay, the case of A. And before you start panicking, just watch what I'm writing down here. concentration of hydrogen fluoride times the concentration of H3O plus divided by, I did that wrong. Concentration of fluoride times the concentration of hydronium ion divided by the concentration of hydrogen fluoride divided by the concentration of water. Now, in practice, you wouldn't write it exactly this way. You wouldn't include the concentration of water because the water is going to be in a very high concentration, and it will effectively not change. Of course, it will change by very small amounts because of the hydronium ion, but it's going to be it's not going to be much. So it's taken to be constant and it's absorbed in K sub A. Don't worry about that. Just look at the structure of the equation. These are the products. These are the reactants. So you have the concentrations of the products are multiplied together to give you a product. The concentration of the products are multiplied together. So you've got that time, the fluoride times hydronium, and it's divided by the concentration of hydrogen fluoride times the concentration of water, which are the reactants. Okay. Now, we're only going to look at this form if you have things like, if you have reactions where there's coefficients on the reactants and products, then you're going to start having exponents on the concentrations, and we're not going to worry about that right now. But anyway, the reasoning is going to be the same if you ever get to that point, if you ever do that. This gives you a nice little way of predicting which way a reaction is going to go if you change the concentration of any of these four quantities. Now, we're going to be talking about, we're going to be doing something in a little bit where what's going to happen with changes of concentration. Think about this. If you have something at equilibrium, you're going to have whatever these concentrations are. This fraction, this fluoride times hydronium divided by hydrogen fluoride divided by water, is going to equal to a constant. And if you disrupt that, you add fluoride, you add hydrogen fluoride, you take fluoride out, you take hydrogen fluoride out. Usually you're really not going to be doing much with the hydronium and water, but in principle, if you were asked that question, it will work the same way. What's going to happen? Okay, let's say you add reactants, add HF, and we're going to go through this again. You add HF, okay, this number is going to get bigger, which means this quantity, this K sub A, well, it's no longer K sub A, it's going to be the quotient of these things, but it's going to be a smaller number. And in order to compensate, you're going to need to generate more fluoride and hydronium ion in order to get back to the K sub A. And the same way, if you remove fluoride, you add hydrogen fluoride or remove fluoride, you're going to make this number smaller, and you're going to drive it towards products. Bigger K sub A is favoring products. So if you have to move in the direction of K sub A, you have to increase it. You're going to need to generate products. And of course, the opposite is true if you're talking about the reactants, changing the concentration of reactants. Okay, so keep that in mind. That could help you if you knew that relation, if you knew that basic equation, and you have that in front of you when you're asked equilibrium questions, you might have a little bit easier time generating the correct answer. Okay, so a little more on equilibrium. You see at equilibrium here, they have this double water tank set up, and I'm not crazy about the way they did this. you could uh, you could say that the way it's drawn, that it might not actually go to that position that it actually that's actually shown in the third diagram, but we'll let it go. You see an initial. This is essentially Le Chatelier's principle, but you see an initial condition where you have two tanks which are attached by a channel, by a tube or some sort of channel between them, and the amount of water in there is enough to get over the bottom, to actually get through the channel. So what happens is, you probably would guess, is that the level of water is going to be the same in both of the tanks. It makes sense. That's nothing that would surprise you. But if you magically generated the situation in the second diagram, where you're adding water to tank A, and you just can get it frozen there the way it is, and of course there's some inlet for air at the top. You need an inlet for air at the top of both of the tanks, but let's say there's a way of air escaping so that the pressure of air doesn't affect this at all. And you suddenly open the middle channel, you're going to get to a situation where the water levels are equal again. So what you've done is you've upset the equilibrium by adding water to one side. You can call that the reactance. And when you allow the system to proceed to equilibrium, you get to a situation where where the water levels are equal in both. So you put a stress on the system, and the system has reacted to relieve that stress. That's what Le Chatelier's principle is. You change conditions. You change a set of conditions when a system is at equilibrium, and you're no longer going to be at equilibrium. So the system is going to react to restore the equilibrium. So we mentioned this. This is the kind of situation where that equation I showed you would help. So let's given the equation, adding more hydrogen fluoride, it says it increases the concentration of the hydrogen fluoride if you add it. So it's going to put a stress on the system that's relieved by increasing the rate of the forward reaction. So let's go back here. Oop, wait a minute. No, I don't have to do that. I have that on the whiteboard. I can go to the whiteboard. I forgot. Okay, you see the whiteboard. You increase the reactance. I said they increase reactance. So see, increasing more HF. What happens? You add hydrogen fluoride. Don't worry about the fact that the reactants are in the denominator. You could flip this thing over, and you could write this equilibrium constant as for the reverse reaction, and you would do the same thing. You add reactants. You add this. I don't want to do that. You add reactants. Let me change this. Your reactants are down here. This gets bigger, so this gets smaller. Let's not call this Ka, let's just say Q. This gets bigger. This is no longer K sub A. This is now, let's say, is some quotient, okay, which is smaller than K sub A. And to make it bigger, what do you have to do? You have to add products. So you don't have to add the products. The system itself is going to add the products, the fluoride and the hydronium ion, in order to bring this Q back to K sub A. And the same thing's going to happen if you add fluoride. It's going to go to reactants. You add fluoride here, it's going to drive it in the reverse direction. And the same thing about removing stuff. Okay, so it says it's going to go, increases the concentration. It's going to put a stress on it. It's relieved by increasing the rate of the forward reaction. You add more hydrogen fluoride, you're going to make that quotient smaller. So it's going to have to get back to the correct level by the reaction going forward, according to the way it's written. More fluoride and more fluoride and more hydronium ion. You remove some of the hydrogen fluoride. Let's go back here. It's going to go in the other direction. Okay, let's look at this. Let's go back to this. Now, if you remove some of the hydrogen fluoride, you make this smaller. Okay, remove. You're at Ka and you remove some hydrogen fluoride. Well, Q gets bigger than K sub A. So what are you going to do? You're going to go from products to reactants. That's the way equilibrium works. It's a simple concept, but the math, when you really get into mathematics, which we're not going to do in this course, it can be complicated, but it still, Le Chatelier's principle is going to predict which way it's going to go, in what direction. It might not give you the exact numbers, but it's going to tell you how it's going to change. So let's go through some more here. We've given the equilibrium, adding more equilibrium reaction, adding more fluoride. Well, you add more fluoride, that's a reactant. So more reactant means it's going to give you more of the reverse reaction, which is you're going to be increasing, you're going to compensate for the added fluoride by increasing the concentration of the reactants. So hydrogen fluoride, that'll increase. So the addition of one or more products to the system will cause their system to shift in the direction of the reactants. What does previous one say? Removing some of the reactant causes the system to shift in the direction of reactants. Well, both of these are shifting in the direction of the reactants. You remove reactant or you add product, you're going to shift in the direction of the reactants. So here's a slide that is undoubtedly in your text. Let me just get the... Yeah, it's on page 336 of your text. I don't know where it is in the e-text, how they work that. But you add reactant, you increase products. You remove reactant, you decrease products and compensate by shifting towards reactants. You add a product, you're going to shift to reactants. You remove a product, you're going to shift to products. There's going to be a shift in the reaction. However, that equilibrium constant, once the system has adjusted such that that product is that constant, it's going to be it's going to give you that constant. So that equilibrium is going to be a fixed point given a set of temperature and pressures, concentrations, and it can be a pretty strong driving force. And a lot of biochemistry, by the way, is going to be, you might see this, you might realize it, and if you don't, I'm telling you, a lot of it is to drive reactions in the opposite direction of the way they should otherwise go. That's why you're going to be you generate energy for biosynthesis, so the body can make carbohydrates, make fats, make proteins, and so forth, which are inherently less stable than the products of combustion. And metabolism or catabolism is largely doing combustion, generating energy. Your movements, you get up and walk across the room, or you run a mile or something like that. You're using energy. You're actually burning carbohydrates or fats and other things to carbon dioxide and water. So biosynthesis is the whole idea, is to drive all that uphill, is to create all these things. So it's against the equilibrium constant. Okay, a few other things here. We talked about hemoglobin in the first place. This is an equilibrium reaction, hemoglobin and oxygen going to oxyhemoglobin. If you take hemoglobin and you expose it to a certain level of oxygen, then it will absorb oxygen. It will bind oxygen to a certain extent, and it's going to be going back and forth. When the oxygen level's high in the alveoli of the lung, after you've just taken a breath, the reaction shifts in the direction of the product oxyhemoglobin. You get into the tissues. Now, the tissues, they have cells that contain mitochondria that are doing oxidative phosphorylation, that are consuming oxygen. You have a low oxygen level, and this process is going on all the time. So you need to keep replenishing the oxygen. And so they bring the oxyhemoglobin brings the oxygen in. It gets into the areas of these tissues where the oxygen concentration is low. It gives up the oxygen, and it moves on back to the lungs to pick up more. Actually, the hemoglobin does other things too, but we'll worry about that another time. And at 18,000 feet, they say you go above sea level, this is going to start happening above sea level, although hypoxia is going to start taking place at a pretty high elevation. You get 29% less oxygen, and you could experience hypoxia. You've heard about, and they show you the symptoms of hypoxia. If you are an athlete and you're going to train in the Olympics, like has happened occasionally, the Mexico City Olympics back in, I think it was 1968, I'm not really sure, there was televised Olympics were relatively new, only started in the 50s. And you'd hear people talking about how unfair it would be for some of the countries to have an advantage of being able to train at altitude, because Mexico City is a fairly high elevation. And the American athletes would train in Denver because of the elevation there. You can become acclimated to that. What happens is your body generates more hemoglobin, more red blood cells, more hemoglobin, so your blood can carry more oxygen is what will happen. That takes a little while for this to happen, but it can. So you see, you're actually, there's different ways of adjusting Le Chatelier's principle. You can either, well, you're going to decrease the amount of oxygen that a certain amount of hemoglobin is going to be able to handle. But then if you train at altitude, you actually get a situation where your body can actually carry as much oxygen, although you're really not changing that equilibrium. You are changing the equilibrium. You're adding hemoglobin. So you add hemoglobin, you're going to shift it towards oxyhemoglobin. And if you see, what you're doing is you're removing oxygen and you're adding hemoglobin, and the two are compensating for each other. But that's a little more complicated, but you should be able to understand that after you realize this slide, after you go through the slide and realize what's happening. So let's go through a couple learning checks. Okay, an important reaction in the body fluids is this one, which is carbonic acid reacting with water to give hydronium ion and the bicarbonate anion. Bicarbonate is one of those polyatomic anions. Now, you use Le Chatelier's principle to predict whether the system shifts in the direction of products or reactants for each of the following. Doesn't have to be complicated. Does it shift in direction of products or reactants? In other words, when you make that change, does more product form or does more reactant form? Okay, add some carbonic acid, H2CO3, aqueous. Okay, what's going to happen? You're adding reactants. So you already have equilibrium. You've got a certain amount of reactant there. Now you add reactant. If you add something, the equilibrium is going to shift in the direction of the other thing. So that adding carbonic acid should shift it towards products. The next one, removing some bicarbonate. Here you added reactants in the first one. Now you're removing products. If you remove something, the equilibrium is going to shift to replace it. So if you remove a product, that too is going to shift in the direction of products. You add some hydronium ion. Well, hydronium ion is a product. You're adding product. You're adding the hydronium ion. So what's going to happen there? You're going to shift to reactants. So let's see if I got that right. I said products, and reactants. Okay, concentration of hydrogen or carbonic acid increases, so you increase the products. It increases the shift of the system to reestablish equilibrium, and you do that by increasing the products. And again, same with B. You're doing the same, you're doing something similar. You're generating an excess of products, if you think about it. You remove an excess of reactant, I'm sorry. You remove some of the product. You're having the same effect, essentially, as if you're adding some reactant. Think about that. Remember that little equation I showed you, the equilibrium constant. So the system shifts in the direction of products. So you remove bicarbonate by some route, more carbonic acid is going to dissociate to reestablish the equilibrium. And of course, if you add hydronium ion, which is after all a product of the reaction, you're going to shift to reactants. That's how equilibrium works. That's pretty much that's really what you need to know about it. And I'll do one problem here on the whiteboard before I quit. And it's really a similar product to similar reaction, similar process to what you've already seen. Let me erase all this. Wait. How do you get to clear? There we go. Clear canvas. There we go. Okay, this is going to be 1023. This is actually a little bit of a good lead into next week, because we're going to be you're going to start doing some organic chemistry, and you're going to start seeing some other compounds that similar to, but not like, well, at least one of the ones you've seen before, that being acetic acid. This one, using Le Chatelier's principle, predict whether each of the following changes causes the system to shift in the direction of products or reactants. Here's the system. HCHO2 plus, we got to fill some other things in here. I'm just going to get the reaction in first. And it's going to be the double-headed arrow is going to give you CHO2 minus plus H3O plus. And this is going to be aqueous. This is going to be liquid. This is going to be aqueous. And this is going to be aqueous. Okay, you see that looks a lot. That looks a lot like the hydrogen fluoride example and the carbonic acid example, doesn't it? Well, This is formic acid. This is formate. Formic acid is an organic acid. It's closely related in structure to acetic acid. It's named formic for the Latin word for ants, for an ant. It's red ants use it as their venom. So it's an acid. So this is an acid-base reaction. So let's see what happens when we change these concentrations. So we deliberately change these concentrations. Let's add more formate. And this is 1023 in your book. I want to make sure I keep writing this the same way that they do. You add that. Well, what's going to happen? That's a product. You've got product, you add product, and you're going to shift to reactants. By the way, this is the second time I've recorded this, and I've caught myself a couple of times saying reactant when I meant product and product when I meant reactant. So be careful if you're listening to this or watching this. Just be aware that that might have happened. I might have missed one or two of those in here. But the formate, you add formate. Let me. I already told. Let's put the formic acid up here so you don't. So it's not too close to the formate. This is formate here. It's a product. You're adding product to an equilibrium process. So you're going to shift this to reactants. B, removing some of the formic acid. Aqueous. Okay, that's up here. HCHO2, formic acid, you're removing it. Okay? You remove a reactant, you're going to shift to reactant. You're going to shift pretty much to whatever you're removing. So if you're removing a reactant, you're going to shift to reactant. So this is going to be shift to reactant. Let's go to C. Remove some hydronium ion. Well, what you're removing, I just said what you're removing, you're going to shift to that. And hydronium ion, as you see here, is a product. So you're going to shift to products. We have one more here. So let's shift this up just a bit. Go back to inking. D is add more formic acid. That's reactant. So if you add something, you're going to shift to something else. This is a reactant, so you're going to shift to products. Now, the answer to this one is in the back of chapter 10. I'll let you take a look at it. I'll let you work through what I just did and see if I got it right. I'm pretty sure I did, but if I didn't, let me know. It'll happen. In fact, the first time I did this, I was I was calling everything reactants, and I realized that wasn't too good. So, but now this should be the correct answer. That's the way you work with equilibrium problems. That's the way you work with Le Chatelier's principle. A change in the conditions. If a system is at equilibrium, a change in the conditions, the concentration of reactants or products, is going to put a stress on the system, and the system is going to adjust to compensate for that stress. Okay, that's all I have now. This went a little longer than I thought it would, but this is an important topic, so it's good to get this down. It'll make it a lot. It'll make things probably a little bit easier when we get into biochemistry. We'll see you later.